Welcome everybody to the third talk of the fall for Math Mornings. This time we're happy to have Jessi Cisewski.
Yes, that was great. Yeah, excellent.
From the Statistics department. She's one of our bright young faculty in statistics. Who's going to give us a talk about the statistics of the universe, aspect statistics. And I wanted to say statistics is an old subject. It's always had connections to mathematics, of course, because it's the study of data and how we interpret and understand it. And in recent years, I think these connections have deepened, and there's a lot more mathematics and computer science that kind of is incorporated into what statisticians do. At Yale, we have the kind of growing group called the data science program that includes the statistics department and people from other departments. And so it's pretty exciting, and I hope you enjoy what Jessi's going to tell you about it. So thanks.
Thank you, and good morning, everyone. It's great to see so many of you here today. Indeed, I'm going to talk a little bit about this area called astrostatistics. And so, as you might imagine, it's statistics for astronomy, astrophysics, cosmology. So statistics and machine learning and computer science and applied math are all needed to do various things in astronomy, especially as we're collecting more and more data. The problems and the models are becoming increasingly complex. And so the area of astrostatistics has formed to help fill the void of statistical methodology that's needed to address these scientific problems. And so some of the problems in astrostatistics are related to things like finding or detecting exoplanets. So exoplanets are planets orbiting stars outside our solar system. And once we've found some exoplanets, how to characterize and describe their populations. Some other problems are dealing with the large-scale structure of the universe. How can we pull information from that structure and understand what's going on, the physics of our universe? Some problems are trying to classify objects. So is an object that we see, is it a galaxy? Is it a star? Is it a quasar? What is it? Or even if we know it's a galaxy, what type of galaxy is it? Is it a spiral galaxy? Is it some abnormal shaped galaxy? Are they two galaxies merging together that makes it a very distorted object? So there are lots of problems in astronomy, astrophysics, and cosmology that require mathematical methods. And so what I'm going to talk about today is one particular problem, which is trying to understand what the distant universe looks like. And so we're going to have to, in order to understand the statistical methodology, first understand a bit about the data. So I'm going to begin with an overview of some topics in astronomy that's going to lead us into how we get this particular type of data. And the data are actually quite unusual, as we'll see. And then once we have the data, how we can actually produce a map so we can get a picture of what's going on in the distant universe. And of course, as I continue, if you have questions, just raise your hand or shout out your question. So we're going to begin with, actually the whole discussion is going to be trying to address a question: what does the distant universe look like? Okay, the issue is that we can't see the distant universe. So we can see some objects that are nearby, but as we move further away from the Earth, the objects have to be very, very bright in order for us to see them. So it turns out that we cannot see the distant universe, so we should just go home and forget it. We're never going to know what it looks like. Of course, that's not the answer. We'll get to how we can actually figure out what's going on in the region of the universe that's really far away. But first, we have to figure out, what do I mean by really far away? That seems quite arbitrary. So we have to have some notion of distance, and many of us are familiar with this closest star to the Earth. This closest star to the Earth is what? Does anyone know what that is? Yep. The sun. Excellent. Yes, the sun is the closest star to the Earth. And so the distance from the Earth to the sun is 1 astronomical unit. That's just by definition. That's just saying we're going to define that distance as 1 AU. That is approximately 92 million miles. Maybe some of you in your physical education classes have had to run 1 mile, right, where they time you and maybe you have to do it once a year. So imagine 92 million of those. So we have miles, but we can also look at it using a different unit of distance, and that has to do with how far light can travel within a particular amount of time. So it turns out that the sun is 8 light minutes from us. So if the sun suddenly shut off, we wouldn't know it for 8 minutes. Okay, so that gives us a sense of distance to the sun. But we are also within this larger object called the Milky Way. So our solar system is a part of our galaxy. Our galaxy is the Milky Way. And this is a side image of what the Milky Way might look like. So we have kind of the center of the Milky Way, and then stars and star systems that are orbiting, and then lots of dust and things. It turns out that the Milky Way is about 100,000 light years across. So from one end to the other, it's 100,000 light years. So 1 light year is a distance that light could travel in 1 year. And then actually astronomers typically don't use the units of light years. Typically what they use is something called parsecs, where 1 parsec is about 3.26 light years. Okay, so the 100,000 light years across is about 30 kiloparsecs across, approximately. So if you ever talk with astronomers, they're going to likely communicate distances in parsecs, kiloparsecs, megaparsecs, gigaparsecs, depending on what type of astronomy they're doing. Our solar system, so we, as part of our solar system, are about 8 kiloparsecs from the center of the Milky Way. Okay, so if you were ever to see the center of the Milky Way, that would give us a distance of about 8 kiloparsecs. Okay, so if we move out a little bit further, the Milky Way is a part of another group, which is called the local group, which is a gravitationally bound collection of objects. And within this local group, we have our Milky Way, and then there's another Milky Way type galaxy called Andromeda. And the distance then between our Milky Way, our galaxy, and this Milky Way type galaxy is about 2.5 million light years away. Okay, so 2.5 million light years away is about 780 kiloparsecs. Okay, so the distance between Milky Way type size galaxies, we can say on the order of hundreds of kiloparsecs. But we're going to actually be moving further apart, and we're going to be talking about the units of distances between galaxies that are not directly gravitationally bound. And so in this image, we see a bunch of different galaxies, and the distances between galaxies would be described on scales of megaparsecs. Okay, so that's going to be the scale that we're considering. And so we want to understand what's happening in regions that are megaparsecs away, even more than that. But the problem is that, as is going to be depicted in this picture, so suppose that we, in the Milky Way, are at this tip. So we're standing here and looking out at the universe, and we're just cutting out a slice. And within this direction, we're just picking out where the various galaxies are. So each point on this image is a galaxy. And so what happens is we're here, and then we start to move further and further away from us. And perhaps you can see what's happening. In this region, it seems like there's a denser collection of galaxies. But as we move further away, it seems like there are fewer galaxies within that same amount of space. right? So we have this problem that either, one, it could be that there are simply fewer galaxies further from us. That's one option. Or it could be that we can only see the really bright galaxies that are far away because the other galaxies are not bright enough for us to see them or detect them. Okay, so it turns out that the second point is the case, and the issue has to do with a property of light. So light, as you may have guessed, is our source of information about the universe. We understand what's happening in the universe due to the light that we're detecting. But the problem is that the further away an object is, the dimmer it appears to us. Okay, so the apparent brightness, so how we perceive the object, is proportional to its actual intrinsic brightness, which is the luminosity, but it's divided by the distance squared. So the further away you get, the dimmer an object is going to appear. Okay, so if you ever take a flashlight and set it down and then kind of step back and see, you'll see the light spreading out. And so it's getting dimmer when you're further away. So that's what's happening with galaxies as well. When galaxies are really far away, they seem very dim, maybe so dim that we can't even see that they're there. There's going to be another property of light that's going to be important for the type of data we're eventually going to be looking at. And this property is that light gets redshifted or blue shifted. So what do I mean by redshifted and blue shifted? Well, if the source of the light is moving away from us, the light that's emitted from that source, it turns out the wavelength gets stretched. So the wavelength gets longer. If the source of the light, like this, is moving towards us, the wavelength emitted, the wavelength of the light that's emitted from those objects gets crunched. And so the wavelength gets shorter. So we have red-shifted light and blue-shifted light. This is actually something that we've all experienced just driving around. If you ever hear a police car or an ambulance coming from behind you. So the same thing is happening with sound waves. When the ambulance is coming towards us, it seems very high-pitched, right? So that's actually, the sound wave is getting blue-shifted. It's getting crunched. And so it sounds the wavelength gets shorter, and so a higher frequency. But then once the ambulance passes, it kind of fades away because it's getting redshifted. The sound wave is getting stretched. Okay, so the same thing happens with sound waves as light waves, and it turns out that this is going to be really helpful for us. So the redshift of an object, so imagine we have a galaxy some distance away. It turns out that we can figure out how much it's been, the light has been shifted if we knew so we can observe the light, so we know the wavelength of light that we observe. If we somehow knew the wavelength of the light that's emitted, we can figure out the redshift. Okay, the redshift is going to be useful for us because that's going to be it's going to be a proxy for distance. If we know the redshift, then we have a sense of how far away the object is from us in the universe. Okay, so all we need, the takeaway from this is really just that redshift tells us about distance. And we can see it better in this picture. So redshift, cosmological redshift in particular, is important because objects are moving away from us at an increasing pace. So it's accelerating. The expansion of the universe is accelerating. And so the 2011 Nobel Prize in Physics was awarded to the astronomers who were able to figure this out. And so for us, what happens is, so imagine we have these two galaxies. One galaxy has emitted light, but as time continues, the objects are moving apart because because space-time is expanding, and so the light wave begins to get stretched. So here you see that the wavelength from peak to peak is a particular length. And then as time continues, so we see time increasing, the wavelength, so from peak to peak, is further apart. And then by the time that light reaches this other galaxy, the peak to peak is even further apart. Okay, so this is cosmological redshift. So the redshift that's due to the universe expanding at an accelerating rate. Okay, so we see that this picture again, we're here, so the Milky Way's here, and as we get further away, this is increasing redshift. This is a redshift of 0.1 and 0.2, and we see on the right side the units in, or the distance in light years. So 1 billion light years, 2 billion, 3 billion. And you see that even within this space, we see a depletion of galaxies. Again, that's due to the inverse square law of light. And this is just highlighting, if we look at the observable universe, we're at the center here, and the 3D region. All right, so what do astronomers do? Since we can't see objects that are really far away due to the inverse square law, well, sometimes what astronomers do is they simulate data. They make fake data and just work with the fake data as if it's real data. So some of you may have seen pictures like this before, maybe, maybe not, but this is our simulated universe. This is based on the Millennium simulation, and the matter or structure where we would find galaxies is along the lighter regions. And then where we see the darker regions, those would be cosmological voids. So where there's a lower density of matter. Okay, so this is great. We, with these simulations, so with these fake data, astronomers build in what they believe to be the physics of the universe, run the simulation, and get this picture. So they have a sense of what does the large-scale structure of the universe look like, based on our best guess at various physical properties. But we'd like to do a little bit better than just looking at the fake data. We'd like to see what the actual distant universe looks like. Okay, so the question that we asked at the beginning, what does a distant universe look like? Problem, we can't see things that are really far away. It turns out that there are some objects that we can see that are very far from us. And these objects are called quasars. So we have this image here. Where this arrow is pointing is a quasar. All these objects that are present, some are galaxies, maybe some nearby ones, depending on what direction we're pointing, could be stars. But just from looking at this image, we couldn't tell how far away the objects are. It turns out, using some other data, they figured out that that is a quasar. So what is a quasar? A quasar is, so the name quasar comes from quasi-stellar. So until the 80s, it was believed that quasars were just some interesting type of star. And actually, these would be some examples of quasars. They are super luminous objects. They are thought to be at the center of really massive galaxies. So at the center of really massive galaxies, we'd have black holes. These black holes, if they start accreting material, so if there's any loose gas or other sorts of substances that might be nearby, the black hole starts to kind of make that substance move really fast, and it gets extremely bright. So a number of these are artists' renditions of what a quasar is, but that's real data. So these quasars are thought to have as much energy coming from it as up to 1,000 times the energy output of our entire galaxy. And so it turns out, again, that these are extremely bright. And because of their brightness, we're able to see quasars that are very far away. And that's going to be helpful for, as we'll see. We, in our Milky Way galaxy, do not have a quasar, which is good. But some think that, so Andromeda, which we saw, is a galaxy that looks like the Milky Way, that the Milky Way and Andromeda are approaching each other, and we could get our very own quasar in 3 to 5 billion years. We'll see. We're not sure, but it could happen. Okay, so why are quasars useful? So this is where we're going to start getting into our data, and the data are interesting. Actually, I find that the novelty of thought required to figure out that this type of data would be helpful is quite extraordinary. So quasars are great. They're very bright. Even better, we have observations of quasars. But quasars are just point sources at various distances, right? So quasars just tell us about what's going on at that particular distance. But we want to know what's going on between us and the quasar. And so it turns out that if you imagine that these little red dots here are quasars, and then this is like the simulation data I showed you. So this is just for illustration purposes. But the light from the quasar travels through the universe to get to us, right? So somehow this light coming from these very bright objects travels through the region of the universe that we're interested in. And it turns out that as it travels through the universe, it leaves a signature of the universe between us and the quasar on the light that we measure at this end. So let me say that again. We're somewhere over here. We see these quasars, and we're measuring the light output from the quasars. Okay, so each quasar gives us a spectrum of light. And that light actually has a signature of the universe. I'm going to call it the intergalactic medium, the IGM, the stuff between galaxies. The stuff between galaxies leaves an imprint on the light we get from the quasar. So if we have light from a quasar, we know something that's going along between us and the quasar. It's kind of amazing, actually. So let's get another picture of what's happening. So we see the moon. Maybe tonight you'll look at the moon, and if there's any cloud covering, you'll see that the light coming from the moon is traveling through the cloud. It's the same sort of idea that we're going to get from the quasar's light. It's going to travel through neutral hydrogen. That's going to be the type of gas substance that we're going to be interested in. So imagine that this is our quasar. It's going to travel through the stuff of the universe, and we measure then the light that's traveled through the stuff of the universe. Okay, so here I am showing you two spectra. So what is a spectrum? We have the wavelength of light. So we saw some of those pictures where you have a light wave. The wavelength is the distance from peak to peak of the light. So along this horizontal axis, it's just how long that peak to peak distance is. And then the height is intensity. So we have coming from the quasar light of different wavelengths. And this is telling us about the distribution of that light. So here are two different quasars that have been aligned in a particular way. So we see we have a peak here and a peak here. Can anyone see a big difference between these two spectra? Yes, back there.
The second one seems more intense and has a much larger difference between the top and the bottom.
Yeah, okay, great. So we see these two things, and the big difference is that somehow this one has a lot more going on, right? That's what you're pointing out? Like there are all these different lines. So what this craziness is are dips. So they're dips in the amount of light coming from these wavelengths from these two different quasars. It turns out what you just pointed out is exactly what we need in order to understand what's happening along the line of sight of the quasar. So how is that so? Well, this is what astronomers call the Lyman-alpha Forest. And I'm not sure why they call it the Lyman-alpha Forest, because to me, it looks less like a forest and more like a bunch of grass, right? Like a meadow. So you might call it the Lyman-alpha meadow. But anyway, they call it the Lyman-alpha Forest. And where these dips happen, where the dip happens is where the light coming from the quasar hits neutral hydrogen. The neutral hydrogen absorbs some of that light and leaves an imprint with that dip, right? So at these different wavelengths, the light's traveling through, it hits neutral hydrogen. The neutral hydrogen kind of eats up some of that light, and we get a dip. And then the rest continues along. The neutral hydrogen eats some of the light, and we get a dip. So this is helpful for us because we see the observed wavelength where these dips happen. So this is actually going to be a hard question. I mentioned it in an earlier slide, but does someone recall, or can you think of another property of light that's going to be helpful here? So this is tough. Yes, go ahead again. Yeah.
Light travels the same distance at a certain time.
So you're hinting at exactly what's going on. So it's traveling a certain distance, is what you said, and that's right. So the light's traveling, it gets absorbed, and then eventually we're going to observe the light at one end. But what else is going on? The light is getting redshifted as it travels a particular distance. So we observe where a dip happens. It turns out that since we can observe where the dip happens, once we get the light, we see the observed wavelength, but that observed wavelength has been redshifted. And so we know that where the dip happened, and we actually know something else. We know the property of neutral hydrogen that causes that dip. So we know that that dip should have happened at a particular wavelength. And so because of that, we know the wavelength that should have happened at and where we observe it. So we know the redshift. We know how far away that neutral hydrogen was in order for us to say there's this amount of neutral hydrogen at this spot. So it's due to properties of neutral hydrogen and due to redshift that we can actually get along the line of sight how much light was eaten, which tells us how much neutral hydrogen there is. Okay, so it's kind of tricky, but again, here's another picture. So the light's coming, the light gets absorbed, and the light gets absorbed. So what we actually observe are these regions where the light is absorbed, and then we can kind of back up and go back to where that cloud or where that neutral hydrogen was. So let's look at a little movie here. So this movie is the light traveling from the quasar. It's going through various regions of gas. So we have the quasar distribution of light, and we see these lines appearing. And so the whole spectrum is getting redshifted as the light travels. And so where these dips occur is where there's more neutral hydrogen. And then eventually we're going to observe the final spectrum. So I'm going to play it again, just because it's a quick video. Okay, so the light traveling from the quasar is going through the intergalactic medium. It's hitting various clouds. At some point, we're going to see it goes across a galaxy, which is going to produce an even bigger dip. But basically, so there's that big dip, which is right here. So where these dips happen, travel along with the spectrum. And because of that, we can get the amount of neutral hydrogen that's occurring at a particular distance. Okay. Oops. All right, so So what else do we have here? So we have these different quasar spectra. From these quasar spectra, this one, for example, has a whole bunch of dips in it. It's traveled through a lot of neutral hydrogen, and so it's a very distant quasar, given that it must have encountered quite a bit of neutral hydrogen. So some of the statistical challenges then with using this type of data is we only know what the observed quasar spectrum looks like, but we have to know how much neutral hydrogen was absorbed in order to, so we have to know the original spectrum in order to know how much was absorbed. So there's a statistical problem that I'm not going to address, but that's there, and it's to estimate what the unabsorbed quasar spectrum looks like. All right, so we have now this way of understanding what's happening in the intergalactic medium. We can figure out what the distribution of neutral hydrogen looks like along the line of sight of a quasar. And we also have data on it, and so that's always nice. So what we have in this plot are, if we were to pick a bunch of different directions in the universe, so looking up at the sky, on here, so they don't look like points, but these are actually points that indicate where a quasar is. Okay, so we look in a direction, and if it's black in that direction, then that means there's a quasar somewhere in that direction. Okay, so I'm going to cut out this red region here, and we're going to take a closer look at what's happening in that region. And so I cut out this region, and this is just showing where we would have data. It's telling us within that direction, so that's this RA in DEC, so on the bottom of this plot, that's the direction we're pointing. And then these lines are the lines of sight that have observations of the amount of neutral hydrogen in that particular direction. Okay, so I cut out this little cube, and I just plotted what the data look like. So at each point on this line, we have an estimate for the amount of neutral hydrogen. All right. And so this just shows you, if we were just to look at the top down, we have these collections, or this collection of points. We can also consider cosmological simulation data that's of that same volume. So I said that sometimes astronomers like to look at fake data. We can look at fake data of the same volume as our real data and do a comparison to see if our real data and fake data are if they look similar. All right, so you can imagine lines of sight going through the simulated data. Just going to jump through. Okay, so this is the figure I wanted to get to. So now that we have lines of sight from the quasar, so we have particular locations here, and now I've colored it according to the amount of neutral hydrogen. So we could just say these are our observations. So this is looking at a slice, and then this is looking at the line of sight. We could just say, okay, we're done. We have our picture of what the distant universe looks like. Does anyone here think that this would be sufficient, like just this kind of dotted picture of what the universe looks like? Right? Yeah, I see some shaking heads. Like, what if in the news you say that you heard that there was some astronomers have a picture of what the distant universe looks like, and that's what they gave you? Who would not be happy with that? Right? Yeah. So we want to somehow say, okay, we have this data. Great, we have data. But what can that data tell us about what's going on between the points? Or within the 3D cube, can't this data inform us about the regions where we don't have data? And so that is where statistics can come in, right? So with various statistical methods, we can figure out ways of kind of coloring in this map, right? We want to say, I don't have data here, but I have data around it, and I want those points around it to tell us something about what's happening between it. Okay, so statistical methods can be used in order to do that. And so, but the problem is that when we start using statistical methods, we have various choices that need to be made. And some of the choices are, one, with what method do we use, right? There are different ways of coloring in the empty regions. And so this is to illustrate one way of estimating what's going on between the places where we have observations. So suppose these are our raw data. So I'm just looking at a 2D slice of the universe. So we pick some directions and fix a distance. And what we can do is say that certain regions are going to be something like averages of its surrounding region. Okay, so if this is our data, we might say, we see kind of a blue spot here. That spot is the same as this blue spot, which is this blue spot, and so forth. And we're just going to start kind of averaging over where our data are. And we can do other things with it, but for our purposes, just imagine that we're going to say the data are some sort of local average of the surrounding observations. Okay, so if we make the kind of neighborhood size bigger and bigger, we see that we start to lose the features in our data, and we could end up with something that's really not that revealing about the structure of the universe. So we have different options, different amounts of smoothing that could be done. Does anyone have a sense of which one of these looks the best? All right, you again, yep. Okay, so number one, you think that looks the best. So this is the raw data, and so that can be great as well. It's just our actual raw data is going to have a lot of missing observations. So we're going to want to do some degree of smoothing to also reduce the effect of noise. But that's great. Okay, so this one. Does anyone like this one the best? You like it the best. Why do you like it the best?
I like that one the best because it has much more like loose. It doesn't have much stuff in it.
Ah, okay, so you like the smoothness of it. Okay, that's great, yeah. So this one's appealing, like it looks nice and smooth, because it could be that this is all noise. It could be that the structure that we see here is just noise, and so actually more smoothing could be better. Does anyone like this one the best? No? Oh, yeah. So anyway, there's some decisions that have to be made. It turns out that in practice, we don't just pick the one we like the best, but there are ways of deciding what level of smoothness, what properties, what parameters should be used for the statistical modeling. But it's good to have a sense of what you think should be going on. So if you think that the data are just full of noise, you might think then that you should have more smoothing. And so when you use various statistical methods, you might expect to see a higher degree of smoothing. Okay, great. So this is not something that we need to understand. I need to understand it, but we don't. My point is just that these pictures here were not just arbitrarily designed, but actually there's statistical models that can be used in order for us to figure out a good way of representing the maps that are produced of the distant universe. Okay, so again, don't need to understand this, but I just want to show you that there is actually some equations that come into play for this sort of thing. And at the end, this is what our simulated data would look like, after selecting the appropriate amount of smoothing. Okay, so this is simulated data, and the redder regions are where there's more neutral hydrogen, and the bluer regions are where there's less neutral hydrogen. Okay, and we can look at just a slice. So imagine if I took this cube and cut through it. This is what we see. And because it's an estimate, when you do statistics, there's uncertainty that's present. And so this is an upper bound on the values here. And this is producing a lower bound on the values here. So actually, you can imagine each slice is expected to be somewhere between the upper and lower bound. And this is our best guess at what that looks like.
So that's with some amount of certainty, like 95%
Yes.
certainty that it'll be between that and that.
Exactly.
The middle one's your average, and you're 95% sure it'll be, or 99, or whatever.
Yes, yes. So this would be a 68% interval. Exactly. Yeah.
One standard deviation.
Yeah, one standard deviation plus and minus. Yeah. So they don't look that different because we have a lot of data. But when I look at this, every time I look at this, I just see a running man. Do you see the head and then the arms and then the legs? Like he's kind of like, yeah. So I can't not see it. But so there he is. All right. So that was simulated data. Now if we look at our real observations, this is what we get. So because we had more data with simulated data, because it's fake data and we can produce a lot of it, we get this. But once you start working with the real data, we don't have as many observations. So just to illustrate, so what we're looking for is a map that describes the distribution of neutral hydrogen, so our picture of the distant universe. And actually he's a cosmologist, one cosmologist said that because of we only have a certain number of quasars, it would be like trying to produce a map of the United States only using 7 cities. So that's the sort of number of quasars that we have filling the region of the universe we're interested in. But we can still get these maps. And so with the real data, this is the fit. And then the lower bound, so minus the standard error, and then plus a standard error. So that this is our best guess of the distribution of neutral hydrogen, and if we wanted instead to look at an interval, it'd be somewhere between this one and this one. So we see there's a lot more noise present with the real data. Oh yeah?
So how different are those really, the plus and minus standard? I mean, like, what does that really mean in real understandable terms? Like they could be
Okay, so great.
bigger, wider?
Yeah, okay, great question. So the question is, what does it even mean to have the standard error? So what happens with data, so I'll speak generally and then I'll come back to this. When you have data, there's a certain level of uncertainty that's present, right? So there's some randomness in our data. And so we can estimate what we think to be, for example, the true mean. So imagine that this is just our true mean of this particular region of the universe. But if we observed a different data set, we could get a little bit different of a picture in the data. And if we observed another data set, we would have had an even different, another different picture. And so what this is trying to capture is that if we had different data sets and we did the same thing, so if I produce this fit using a bunch of different observations, which we don't have, but you could imagine that if we did have it, that 68% of the many sets of data that we have, 68% would produce maps that are between this lower bound and upper bound. Does that make sense? Are there other questions about this? So often in statistics, we don't just give one number, one value, but you have some degree, maybe you've heard terms like margin of error and things of that nature. So that's trying to capture the uncertainty that's present in our best guess. So new data sets would produce slight fluctuations. Yep.
Maybe this is the question you're answering, but can you make a map of the United States with 7 cities?
Oh,
When you
yeah.
try it,
Yeah.
do you have a system that you can use that level of uncertainty and recreate something you can compare with something that you know and see how it looks at the end of it?
Yeah, great question. Okay, so the question was, if we wanted to produce a picture of the United States, and indeed we only had 7 spots to do it, I could give you a map. Now, the issue is, if we chose, for example, 7 different locations, the map could change quite a bit. And 7 other locations, and it would change quite a bit. But at least with the United States, we'd be able to compare it to a very dense map. And so we could compare it to the truth with something like the United States. The problem with the distant universe is that we don't have a way to get more observations. So this just ends up being our best guess given the data that we have.
So there isn't any other model system that you could use this technique on and see how it reforms, how well you form that picture?
So we could try in certain regions to get data using other methods. Maybe we can see some galaxies in those regions and get a sense of what's happening. The problem is any other sort of data would not tell us as much about the amount of neutral hydrogen, which is what this is revealing. So let me come back to that in 1 second. And this is actually, so I'm actually here not using the full data, but just a small piece of it. And so actually this is a more recent, just surface of, so I'm cutting out a certain distance and then just changing the direction. And so this particular image was produced by Colin Eubanks from Carnegie Mellon. He's a STAT PhD student. And he's using actually new and more data. And so he's able to get this picture. And he's actually using some different statistical methods than what I was talking about that help to adapt to the design of the data a little bit better and can produce a better picture. Yep.
So you helped us visualize what may be happening there.
Yep.
What is the actual difference between red on one extreme and blue on the other? Is it the difference between 1 atom of hydrogen per cubic meter and 10 atoms per cubic meter?
Yeah, so
What are the 2 extremes that we're supposed to be?
yeah, so what we're actually seeing are the fluctuations from the average amount of neutral hydrogen. So we don't have like the exact number of atoms, but we just know how much it's changing from an average across the region of the universe. So the redder regions would just say that from the average, there's some amount that's more, and the blue will be, it's under less than the average. So it's more fluctuations that we're seeing and not raw values.
Okay, and how sensitive are the fluctuations? Is it 10%? Is it 50%?
How sensitive are the fluctuations? You mean how? Can you say a bit more on what you mean by?
Well, I'm just using English and not statistics.
Yeah.
Is it the difference between, I guess, how, is the difference between like 50% and 51%?
Oh, okay. Okay, I see now what you mean. Like how sensitive? Okay, so how much is it fluctuating? So you're kind of asking. Okay, so what are the raw values here? So I'm not completely telling you the truth because we don't. These aren't even the fluctuations of the neutral hydrogen. It's a function of the amount of fluctuation that gets into more astronomy details, but you can say roughly. It has to do with the column density, and there are details that I'm kind of putting under the rug, just for simplicity's sake. So if one is actually interested in how much these fluctuations are, I can talk to you in more detail after this. But what you can imagine is just as the light's traveling through the intergalactic medium, it's going to there's either going to be kind of wisps of neutral hydrogen or not. And when you hit kind of some of the wisps, some of the light is absorbed, but denser denser kind of clouds of neutral hydrogen are going to produce bigger dips. But I don't have like the raw numbers to tell you, unfortunately. But those are all interesting questions for sure. Anything else about this map? Oh yeah, go ahead.
Why is the area which you have such a random shape?
Oh, interesting. Yes. So why is it cut out like this? That is a great question. Why, for example, is there a little dip here and there and so forth? So this isn't all the data from the Sloan Digital Sky Survey, but what's causing the bizarre kind of shape just has to do with where the telescope is pointing. And so the Sloan Digital Sky Survey points in particular regions at different times of the year. And so the boundary is, there's not going to be a smooth boundary because it's going to depend on where the quasars are. So, for example, right here, there just weren't quasars near that part of where the telescope was pointing. But what also can happen for these weird boundaries is that even if there are quasars within that direction, the Lyman-alpha Forest could be such that either the quasars could be too far away or too close, so that where the Lyman-alpha Forest appears is not within the region, the wavelengths that the Sloan Digital Sky Survey is measuring. So it could be redshifted off where the telescope is measuring data, or it could not have reached that point either. So it has to do with the telescope design, so where it's pointing, and also if there are quasars there or not. So yeah, so there are some interesting boundary issues in general. There are other pieces of this that are just different directions. Another problem that happens when looking at the universe is I showed you a picture of the Milky Way galaxy. And so we're within the Milky Way, and if we were to look at the plane of the Milky Way, we wouldn't be able to see through the disk. And so we're confined also by the fact that we're in this spiral galaxy, and so we can only look above and below where that spiral disk is. So it's kind of interesting. Yep.
That's related. When you use a telescope, is the atmosphere going to absorb the light? So how are you going to avoid the atmosphere?
Oh, yeah. So that's also a problem. So the question was, what about the atmosphere? The atmosphere can absorb light or can cause distortions. So yes, that can happen. So one has to be careful that the portions of the spectra that we look at aren't distorted by extra features due to the atmosphere. So that's definitely something that we have to keep in mind for ground-based telescopes like the Sloan Digital Sky Survey. Some are out in space, like the Kepler telescope. Out in space, you don't have to deal with the atmosphere issues. But yeah, great questions. Is there any? Yep.
Did you say the redshift is measuring light that's coming toward or away?
Yeah, so the redshift is if the source of the light is moving away from us, it gets stretched. And so the quasars are moving away because the universe is expanding at an accelerating rate. So that's what's redshifting it.
And then the blue is moving toward us.
So if the source was moving towards us, then it would get blue shifted. Yep.
And does that change because things are moving in a different way and there's retrograde motion and there's because where we are is not dependent on how things are moving. So if something's moving toward us, we could also be moving away as well.
Yes, yeah. So okay. So indeed, there are issues. So the distances that we're considering are so far away that we wouldn't notice any backward and forward motion with this data. But if we were looking at the nearer universe, then what can happen is objects, for example, let's just use stars as an example. stars are, sometimes you have binary star systems, and so you get these local motions where stars are orbiting each other. And so at some point, the star is coming towards us, so that would cause a blue shift. And sometimes they're moving away, so it causes a redshift. So as a general problem, when you're dealing with the more local universe, those sorts of issues, so those we'd call Doppler shifts. So those are shifts due to the motions of the objects. When we're at these very distant distances, local motions aren't going to cause any problems. Anything else? All right, so just then in conclusion, what we learned about today are that, one, trying to figure out what's going on in the distant universe, so at higher redshifts, is tricky because we can't see those objects, but that there are some objects that we can see, like quasars, and so they can help to give us the beginnings of a picture of what's happening in the regions that we can't see. And so, again, the quasars travel through the intergalactic medium. We see these spectra. The spectra have the Lyman-alpha Forest imprinted. And from that Lyman-alpha Forest, we can get a sense of what's going on along the line of sight. And then from those lines of sight, we can try to produce a picture of that distant universe. And throughout the whole thing, there are different statistical methods that are involved that help us to get this picture. So I'll end there. So thank you so much for your attention.
Thank you very much.
Great, thank
Are there any other questions? There were a lot of questions before. Any more questions before we go on?
You mentioned at the very beginning that because we can't see, or even though we can't see a lot that's in the distant universe, doesn't mean there's not necessarily as dense as the air around us.
That's right.
Is it possible, because of the time that it's taken the light to get us, that when that light was emitted, there just actually wasn't as much out there?
Yeah. So the question is, could it still be the case that there are, for example, fewer objects far away because it's an earlier universe? And yes, yeah, that certainly could be the case. We're not expecting a uniform density or distribution of galaxies between us and the very early universe. That's for sure. The issue is just that we know due to our telescopes that we are missing some galaxies. And so we just want to make sure to account for the fact that some are missing due to the inverse square law of light. Yeah, so there's some magnitude limitations. Yeah. Yeah.
So for the young people in the audience, I was kind of interested in your trajectory. So were you interested in mathematics and statistics and then found an interest in astronomy, or were you interested in astronomy and then realized you need these tools and then went to statistics? How did you end up where you ended up?
Yeah, okay, so when I was in middle school, I was just fascinated by astronomy. I mapped the northern hemisphere star constellations on my wall with the glow-in-the-dark stickers. Like, I just thought space was really cool. And then in 9th grade, I did a science fair project theorizing black holes as the center of galaxies, because that's when they were realizing that black holes could be the center of galaxies, and I thought that was neat. But then when I went to college, I did a Bachelor of Science in Math, and I, for some reason, didn't think any more about astronomy other than I was fascinated by it. And I actually went and worked as an actuary for 2 years before going to do a PhD in statistics at the University of North Carolina at Chapel Hill. And so still I wasn't thinking about astronomy, but as I was pursuing my PhD in statistics, I saw a bulletin from the Institute of Mathematical Statistics. And on the cover of that bulletin said, "Statistics and Astronomy." And I got tears in my eyes, and I just was like, oh my gosh, of course, astronomy and statistics. That makes so much sense. And so then I started trying to pursue that. My dissertation topic was already set, but I was able to take some astronomy courses, and then my position after I finished my PhD was at Carnegie Mellon, and they have at least 5 statisticians who work in astrostatistics. And I went there because I wanted to get involved in it, and so that was a great place to learn about astrostats. So I went from being interested in astronomy to really just pursuing math. and then statistics, and then finally some astrostat. So.
The slides you show us remind me of recent election. We see blue, we see and also remind me in chemistry, in physics, we talk about the Brownian motion, basically also related to statistics.
Yeah.
So in general, I believe there are some connections. There were some disconnection.
Yeah.
But the overall, what's the direction for the statistics as a subject to develop in the future?
Okay, so the direction of statistics in general. So statistics is actually quite interesting because there are some who just are interested in the mathematical properties of various statistical methods. And so statistics has a very theoretical side. It also gets into probability. Some probabilists are in math departments. But then you can get to the very applied side of statistics and get into data science. And so these days, this whole kind of data science kind of push really across the country in various areas has been making kind of a presence in statistics. So what you'll find with statisticians is that many statisticians have particular applied fields of interest. Like for me, I like astronomy. Some get into neuroscience. You have biostatisticians who deal with tons of different problems in biology, from kind of clinical trial type things up to like neuroscience even, and genetics and all of that. So it does seem that there are a lot of statisticians who are getting involved in more applied areas of science. So we see that there's a lot of discussion in the statistics community about data science, even just what is data science. Various people have different perspectives. Many statisticians will say, well, data science is just statistics, and then computer scientists say, well, it's computer science. And so
following what you mentioned, nowadays I learn many places, including university, that talk of big industry institutes. They talk about big data.
Big data, yes, yes.
So
yeah.
This certainly will play a big role in big data analysis.
Yes, yeah. So big data is certainly a buzzword, maybe more than a buzzword, because it's sticking around and it's probably going to be around. So the issue, or maybe we'd call it the opportunity, is that we're getting more and more data in all these different areas. So in astronomy, various telescopes are being commissioned that's going to bring in just tons and tons of data every night, and we don't know how to deal with all that data. And then, like Google and all these other kind of companies that are gathering data on people that use their products, they get tons and tons of data that they need ways to deal with it. So those are all problems that statisticians are worried about, computer scientists are worried about. Machine learning is kind of an area within computer science. They're worrying about it. So these are all challenges that will be around for quite a while, because as we continue along, who knows if big data will ever disappear. It'll just get bigger, and so we'll just continue needing more methods to work with massive amounts of data. So yeah, those are definitely challenges, not resolved. Yeah.
How can we see data so far away? Like, they're light years away, then how can we even see them? They're like more than 92 million miles away. How can we see them with a super giant magnifying glass?
That is such a great question. So the question is, how can we even see these objects that are so far away? That's exactly right. We need these super giant magnifying glasses, and that is what they have. They're telescopes, and these telescopes act like what you might imagine a big magnifying glass would act like. And it's this telescope is reading in the light that in the direction that it's pointing. And so these instruments are sensitive enough to be able to detect the various light sources, and they can get more light if they point at an object for a longer amount of time. So yeah, telescopes and engineering and how those are designed are very interesting problems, and it's quite amazing that they can even gather data from so far away.
But how can it gather so far away, even though like it takes even though we use one type of thing, it still takes the same amount of time to reach, and it still takes the same amount of time, even though that you use something.
Yeah. So are you saying that these objects are so far away and it takes the light so long to reach us?
Also, like when we use telescopes, wouldn't it also be the same time that the light would go down? And we see it, and why wouldn't the light? Then why would the light reach our eyes? And then if it traveled the same distance in the same time.
Yeah. So these are such great questions. So if you imagine that the distant universe, so the objects are billions of light years away. So if they started emitting light billions and billions of years ago, that light has taken a long time to travel to us. So the light that we see is actually really old light from those objects. So we're not seeing the objects as they are today. We're seeing them as they were billions of light years away, or billions of years ago. Yeah, so, but you also mentioned a really interesting point, and that is, so we know the sun comes up, and when the sun comes up, we don't see the objects, and so astronomers have to wait until the sun goes down to start reading in the light, and so it also turns out that whether there's a full moon or not dictates how good of data they can get. And so there are all these different problems with scheduling when to observe certain regions of the sky and certain objects that are related to the points you just made. So yeah, so it's a tricky problem, but fortunately there are a number of astronomers who have figured out how to do it. So good questions.
Maybe one more question, and then we can come up and ask other questions at the end. There's one other question.
Oh, okay, yeah, go ahead.
How can we see the sun so easily, but when we see Mars sometimes we can barely even see it?
Great question. So the question is, how can we see the sun so easily, but Mars we can't really see that well? There are several reasons. I'm going to go back to this picture. Oh, this one. So if we see that the Earth is here. So we see the size of the Earth compared to the size of the sun, right? And then Mars is in here as well. So the size of Mars is so tiny that it's easy for us to see the sun because it's so massive. But it's not just massive, it's very, very bright. And so because it's bright and because it's massive, we can see it very clearly. But Mars is tiny. And it's not bright. It's not glowing like how the sun is glowing.
But if why is Mars so close to the Earth and we can see it not so well, but the sun is a bit farther, so we can see it well?
Yeah. So yeah, it's interesting just because this is actually to scale, and so do you see how big the sun is here, right? So it's really big, and very, very bright. So we can actually see it extremely easily, and Mars is much smaller and it doesn't glow, and so it's kind of like, so if you're in the dark, do you have any glowing balls, where if you hold it under the light and then you go into the dark, you see it glowing, or?
I have toys that are glow in the dark.
Yeah. Okay. So those glow in the dark toys, when you're in the dark, you can see them, right? Because it's glowing and it's easy to see. But if you just took a regular tennis ball and it was dark, you wouldn't see it, right? So because the sun is glowing, it's actually a liquid. It's a plasma, and it helps. It shines, but Mars doesn't shine. So it's not always going to be easy for us to see Mars. So yeah, great questions.
Okay, let's thank Jessi one more
Great.
time.
Thanks.